All right, to be back where we were when we ended class on Wednesday, we were talking about applications of logarithms and exponentials and how our ability to solve them now kind of opens up that we can do different things with these same equations that we've seen before. So we were on the banking and talking about earning interest, using these two equations that we've seen before when we have interest compounded either n times a year. So we've seen the words like monthly, meaning n was 12. We might see daily. So that would mean that n would be 365. You might see quarterly, so 4 times a year, and it's 4. The n compounding is how many times is the interest being calculated. For continuous, meaning your interest is always calculated, that's when you use that second equation, A equals PERT. So P, remember, represents the principal, your initial amount, A represents your final amount, how much you earned overall. N, we just said, is the number of compoundings, how many times it's compounded. And then R would be what's your rate. Remember, we want to use it as a decimal, not as the percent. And T here would be the number of years, the time. The variables representing the same thing in the continuous compounding. So if we look at the question that we were on and we say we're going to use this A equals P, parentheses 1 plus R over N, N to the T power, we want to figure out what do when we change this 500,000. We want to go from 25,000 to 50,000. We want to double our money, and we're at 9%, and it's compounded monthly. We want to figure out how long is that going to take. So first thing might be helpful to know is which variable are we solving for? So it says we're saying how long is it going to take? So we're trying to figure out T. T equals what? So we should know what A is, what P is, what R is, and what N is. So A is our final amount, so that's our 50,000. P is our principal, our initial amount, so that's 25,000. R is our interest rate, so 9% or 0.09 as a decimal. And N would be how many times it's compounded each year. So N, it says monthly, so it's 12. So if we write out the equation, 50,000 equals 25,000 times 1 plus the rate is 0.09 divided by 12. And then it's N times T. So 12 times T. So if we're going to solve this, we solve it like any exponential equation. So 50,000, first off, I'm going to simplify what's inside of this parentheses, just so it looks a little bit nicer. So 1 plus 0.09 divided by 12 gives us, in this parentheses, 1.0075 to the 12t. So if we remember, how do we solve an exponential equation? First, get this exponential portion alone. So we need to divide by 25,000. We divide 50,000 by 25,000, that's 2. So 2 equals 1.0075 to the 12t power. Now we have alternative ways. Some people are going to use natural logs here. Some people are going to use logs. And that's what I'm going to do in this case. I'm going to change this into a log. So the log and the base is the same as the base on the exponential. So log of 1.0075, or sorry, log base 1.0075, 2 equals, and the exponent is always what your log is equal to. So this makes sure you should get something. Remember, when you switch forms, you should get something you can actually type into your calculator. So make sure you can do that now. Double check into your calculator, you can type this in. And then how do you solve for t? You take that number that you get from your calculator and divide by 12. Typing that in, and again, make sure you can do that, you should get T is 7.73 or about 7.73. So that represents 7.73 years, 7 and almost 3/4 of a year to double your money if you had 9% interest. And if you have 9% interest, by all means take it, because that's an unbelievably good interest rate for you to have in any kind of savings situation. So the idea is now this banking application, this interest application, you can actually solve for different values that we hadn't been able to solve for, like how long would you need to keep your money in to earn a certain amount. The last growth decay, the last exponential application we're going to look at is a growth decay model. And generally when we use this, we're talking about this generic form, and this equation you'll need to use and know for the quiz. Normally we use this sort of equation for population models, and that's what you're going to be using it for in our case, to model population growth, but also population doesn't always increase. Population could go ahead and be what we call decaying or decreasing. So using this general format and noticing what situation we have, these variables are going to stand for information that we would know if we were talking about population growth, population decay. So if you see this 0, A sub 0, the sub 0 is always telling you that it's an initial amount, a starting amount. So A sub 0 would be your starting, and we're talking about population. So this is always going to be your starting population within a country, or maybe a city, or maybe even a group of animals. Your starting population is going to be A sub, what we call A sub 0. So that means A would be your final population, where you end up after so many years. T is the number that always represents our time. So this is, again, time, and we're going to be talking about in number of years. And the last piece here, this K, which is a new variable for us, we haven't seen in any of the other equations we've done, is a number that represents basically the growth or decay, and so we'll call it our growth or decay factor, telling us how much our population is growing or decreasing by each year. So the rule is, we're going to do an equation that can represent growth as well as decay, is if K is a positive number, in other words, if K is bigger than 0, this model is going to represent a growth of a population. So positive numbers are going to represent growing populations, and negative numbers are actually going to represent populations that are decreasing, or populations that we would say are decaying. So that K value is what controls what our overall result is. So if we look at an actual problem, in hometown USA, the population in 1980 was 32,000, and in 1990 was 37,800. Population is exponential, so we know we're going to use this basic setup. How many people are going to live there? So this is two different questions. How many people are going to live there in 2010? So one important thing to point out is that this T variable represents not the year you're in. It's not going to represent 10,000. It's going to, or sorry, 2010. It's going to represent how many years have passed. So if I'm looking at my initial amount, 1980, the population was 3,000 or 32,000. Then in 2010, T is going to represent how many years have gone by. So that would be T is 30. So just realize that one distinction here. If we're going to represent, so we want to figure out in 2010, what is the population? So let's go through and make our equation to represent what's going on in 2010. 2010, so we don't know the A value because that's our final amount. That's what we're trying to find. But we do know A naught or A sub 0, which would be 32,000. That's where our population is starting. Times e to the, well, it doesn't tell us how much the population is growing by, so we don't know what k is. But we do know that in 2010, 30 years will pass, so t is going to be, we can substitute in 30. Problem with this equation now is that we don't know what the k value is. We don't know what the a value is, and we don't know what the k value is. So it's hard for us, it's impossible for us actually right now to say what the new population is. So what we have to use, and if you look in the question, the first question, up till then, is there information we haven't used? Well, yeah, look at 1990. We knew the population in 1990 went up to 37,800, so we want to use that to help us finish off our equation. Get us enough information so we can figure out what happens in 2010. So if we look at 1990, we consider 1980 our starting point, 1990 our stopping point, 37,800 is going to represent that A value, because that's going to be how much the population was at, the quantity the population was at in 1990. So it'll equal our initial amount, that A sub 0 is our initial amount, times e to the, okay, we still don't know what k is, and if it's 1990, then t must be represented by 10, because 10 years have passed by. So what you notice now, though, is we have only one variable, and that's the variable we need in order to complete our question from 2010. So what we need to do is solve for k. How do we solve for k? Well, get the exponential portion alone by dividing by 32,000. That would be 1.18125 equals e to the, and I'm just going to rearrange those, 10k. If we rearrange this, we've got the exponential portion alone. Let's rewrite this as a log. It'd be log base e, so that means it's ln. Natural log of 1.18125 equals 10k. We want to know what k is. So take that natural log, type that natural log in of 1.18125, find that answer, and divide by 10. And you should get that k is 0.01667, and I'll stop writing at that point. You could definitely round it a little bit earlier, but I'm going to use as much of the number as I possibly can. So now that I have that k value, I can use it, assuming that that k value, that growth rate stays the same, which might be a stretch. We can now use that k value in our problem to solve. So A equals 32,000 times E to the 0.01667 times 30. Type that in and we get population of 52,743.78, but you can't really have 0.78 of a person, so we'll just keep it at 52,743 people. So now we know how many people are living in hometown USA in 2010, and now that we have that K value, we can also solve this second problem. In what year? So we want to know T equals what? Well, they have a population of 50,000 people. So 50,000 people is your final amount, your A value, equals, so this is question 2, A equals, so we start with 32,000, E to the 0.16657 times T. Take a minute, solve this problem on your own, and then check your answer. I already changed that K value to 0.016657, and you should get a T value of, once you solve, 26.8 years, which would put that in 2000.